It's my pleasure to be at this conference for the first time and to talk about recent developments in membrane, and I hope you all can hear me well. Before we dive into the details, I'd like to take a moment to express my gratitude for your time and attention. I truly appreciate the opportunity to share my thoughts on this important subject. Today, I want to talk about recent developments on preparation of nanocomposite membrane for wastewater treatment. Uh, in the introduction, I want to clarify the extent of water pollution and its devastating impact on both the environment and human health. Water pollution is a major global environment problem because it can result in the degradation of all aquatic ecosystem. Meanwhile, our drinkable water source are finite. Less than 1% of the Earth's fresh water is actually accessible to us. Uh, in this study, our primary objective is to address the treatment of wastewater by employing membrane technology. The study delves into the utilization of membrane as a key component in the wastewater treatment process. These membranes play a crucial role in separating impurities, contaminants, and pollutants from the wastewater, resulting in a more efficient and environmentally sustainable treatment method. The properties of the membrane must be able to operate efficiently and for a long time to be used commercially. On this basis, the focus is on improving the properties of the membrane so that it can work with high efficiency and thus have high productivity and at a lower cost. Among the methods used to improve membrane properties are embedded nanoparticles and nanomaterials by surface modification, grafting, coating, and polymer blending. Nanomaterials have emerged as the next generation of materials for high-performance water treatment membrane, offering the ability to address the global water pollution problem. Nanomaterials enhance the water permeability, mechanical strength, separating efficiency, and decrease fouling of membrane. Therefore, nanomaterials offer a new opportunity of the development of water purification membranes that are both high efficient and highly specific. In view of nanoadditives, the integration of two dimensions nanomaterial lead to the formation of interfacial voids between the nanofillers and membrane polymer chains. These formed cavities can promote high permeability than pure polymer. Among these two dimensions nanomaterials, mixing nanosheets have been mostly explored by blending with various polymer materials, followed by phase inversion for preparing water treatment membrane. The introduction of mixing nanosheets to the polymer matrix can sustainably improve the permeability, anti-fouling, and even antibacterial activity. As shown in this figure, mixins are two-dimensional layered carpet or nitrides uh, um, produced by carefully etching away aluminum layers from the max face. As shown in the figure, the formula of mixin is Ti3C2Tx. The Tx for the surface modification like OH, O, and F functional group. These materials are often created by extraction the aluminum layer from the max face. For the synthesis of mixin, we using the delamination process. Mixin was prepared on the max phase substrate as shown in this figure. The etchant solution was pre-mixed and contained ammonium hydrogen difluoride NH4HF2. Then the max phase powder was gradually added and for 12 hours to remove any potential mixing aggregates. The producing Ti3C2 slurry was centrifuged and then in the ultrasonic. Lastly, the final product was filtered with vacuum pump filtration and dried in an oven that was heated to 80 Celsius for 12 hours. The experimental work in the current work, mixing were fabricated and embedded with PVC solution to compare their effect on the PVC bare membrane's performance. The specific and manufacturers of the materials used to prepare the PVC membrane are listed in this table, which is 14 weight percent PVC and 86 weight percent DMAC with the different concentration of mixing nanosheets. For the preparation of the PVC mixing membrane, the polymer solution were cast at 200 micrometer thickness using a motorized film applicator under atmospheric conditions. The performance of the fabricated PVC mixing membrane was examined in BSA, bovine serum albumin, and lead metal ions. The porosity and pore size. The porosity and pore size, the observations suggest the incorporation of mixin significantly influenced the membrane porosity and pore size as illustrated in this figure. This observation suggests the extent of a threshold where mixin enhances the inner structure of the PVC membrane. Beyond this limit, a denser structure may form because of the increased casting solution viscosity, leading to a delayed mixing demixing process. In addition, the hydrophilic character of mixin, coupled with its larger average pore size and broad pore size distribution, primarily contributed to the observed decline in contact angle in the produced membrane. These results confirm the enhancement in hydrophilic properties of the PVC material upon mixin incorporation. For testing performance of membrane, we utilize a custom-made cross-flow filtration setup. This figure describes the schematic diagram of the experimental work. The neat PVC membrane relieved a pure water flux permeability of approximately 128 liter per meter per hour, while the BSA solute flux reached its minimum value of 31. Compared to the other modified membrane, the incorporation of mixin within the polymeric matrix considerably enhanced the pure water flux of the modified membrane up to a certain additives content, especially the N2 mixin nanocomposite membrane, which is containing 0.4 gram of mixin nanosheets, demonstrates the highest water flux rate of 21 LMH. Incorporating 0.4 of mixin into the membrane matrix resulted in significantly higher rejection rate of 99.9% for BSA compared to the pure PVC membrane, which had a rejection rate of approximately 83%. For the anti-fouling properties of the membrane, we investigated using the flow recovery ratio, a parameter closely associated with the irreversible membrane fouling, FRR, was determined by calculating the pure water flux of each membrane both before and after conducting BSA experiments. As illustrated, the PVC membrane exhibited the smallest FRR at 49.9% compared to all other analyzed membrane. Incorporating mixin nanosheets into the polymer matrix significantly increased the FRR of the PVC membrane and also decreased the relative flux reductions. To evaluate the long-term operation of the optimized membrane, 3 cycles of extended filtration tests were conducted for both bare PVC N0 and N2 nanocomposite membrane. As illustrated in this figure, these tests aimed to evaluate the stability and the longevity of the produced nanocomposite membrane over a 6-hour operation period. During each cycle, the process included measuring the flux rate of pure water for 60 minutes, assessing the decrease in flow rate using a BSA solution for another 60 minutes. The control PVC membrane demonstrates a significant and irreversible decrease in flow compared to the N2 nanocomposite membrane which is zero point 0.4 gram of mixin. The percentage of PP ions that are rejected is depicted in this figure. The rejection of PP ions in all membrane modified with mixin exhibited a noticeable and gradual enhancement with each incremental increase in the concentration of additives. Among the evaluated nanocomposite membrane, the zero point 0.4 gram nanocomposite membrane exhibited the highest rejection performance with a rejection rate of 91.03% compared to 60% for the unmodified membrane. The leaching and stability. A mixin leaching measurement was performed to evaluate the leaching of the mixin for the membrane. The leaching figure illustrates the comparison of the percentage of the filler leaching from membrane throughout soak test. In the first days, the experiments, the filler release was increased, but after that stabilized at 5.2% after 3 weeks. The stability of the incorporated mixin nanosheets inside the membrane matrix is crucial for particle application. Regarding to the performance stability and the mixin contaminants issue. The rejection mechanism in the case of BSA is determined not only by size exclusion but also by Donan exclusion. This figure depicts how Donan exclusion operates for negatively charged membrane. Such membrane rejects negatively charged contaminants such as BSA, but allow water to pass through by transporting various solutes and interrupting some ions within the membrane's channel pores. In the case of heavy metals, functional group in mixins such as hydroxyl, oxygen, fluorine can interact with heavy metals ion through electrostatic attraction or chemical bonding, leading to the adsorption of metal onto the mixin surface. In the conclusion, this study presents the fabrication of a novel nanocomposite ultrafiltration membrane by incorporating mixin nanosheets into polyvinyl chloride PVC based on the provided information. It can be deduced that the incorporating of mixin significantly enhanced the permeability, selectivity, and fouling resistance of the developed PVC membrane. This improvement in surface properties can be attributed to the strong compatibility between the mixin nanosheet and PVC chain. The addition of mixin nanosheets in different ratios significantly influence the membrane characteristics and performance. This study shows that by adding of mixin nanosheet to the polymeric membrane in an adjustable and cost-effective, it is possible to avoid the use of reverse osmosis or nanofiltration, both of which require high operation pressure and energy requirements. Thank you.